Hello everybody. This is a video about well-designed databases. There is a related file that goes with this video that I'm using for examples in these slides that you may want to print off and look at while we go through this video. What is a well-designed database? You probably are wondering. Well, features of a well-designed database are there's no data redundancy, there are no inconsistencies, and there are no anomalies, meaning there's no problems. And in this instance, there's no update anomaly, there's no insert anomaly, there's no delete anomaly. Here's an example of a well-designed database. It has 3 tables in it, and this database is to keep track of people who get parking tickets. Since I have paid several $100s in parking fines over the last several years, I consider myself an expert on this database. Let's take a look at each of the 3 tables. There's a car registrations table, which lists each person who has registered a car. And let's assume that a person can register one and only one car to keep this from being too complex. The primary key is the Social Security number. Beneath that is the parking violation codes table. Every parking violation code has a related fine and an explanation, and this table's primary key is the code number itself. If nobody got parking tickets, the only data that would reside in this database would be in these 2 tables. As soon as somebody gets a parking ticket, we insert a record into the parking tickets table. The primary key for this table is the parking ticket number, and you can see that there are 2 foreign keys, one for the Social Security number and one for the violation code, which allows us to create a relationship to the other 2 tables. So now we don't have any redundant data. Everybody's name is listed once, everybody's phone number is listed once, every fine is listed only once. And there's no inconsistent data. I know that every record in the parking tickets table will be related to an existent record in the car registrations table and the parking violation codes table. Let's take a look at the anomalies. There is no update anomaly. If Larry changed his phone number, then we would make a change in one and only one record and one and only one field. There is no insert anomaly. If we added a new violation code or a new car registration, all that would be needed would be to add a record in the car registrations table and the parking violation codes table. What if Jane got another ticket? Well, all we would do is add another record in the parking tickets table. It's very important to remember that the database management system will only allow tickets for people and codes who have related records in the other 2 tables. There is no delete anomaly. The database management system will allow the deletion of the parking ticket 10151, and no other data will be lost. However, the database management system will not allow us to delete a record in the car registrations table or the parking violation codes table because there are related records in that parking tickets table. So how do we get to a well-designed database? The process is called normalization. We start out with unnormalized data, we go to first normal form, second normal form, and then when we get to third normal form, we can consider that we have a well-designed database. Let's go through the parking tickets example. Here's an example of an unnormalized table. This is the same data that we were just looking at, but all of the data is entered into this one table. So, how do we go to first normal form? Well, the first thing we do is fill in all of the empty cells with singular data, and we identify a primary key for our table, and in this instance the primary key is the parking ticket number. In doing so, you can see that we have created redundant data. For example, Jane Brown and Larry Mason's names and phone numbers and license plate numbers are listed in several locations. So to go to second normal form, we want to remove this redundant data. And in doing so, we will take those two people out and put them in a separate table called the car registrations table. And I've added a foreign key to the parking tickets table to allow us to continue the relationship between the parking tickets and the people in the car registrations table. In going to third normal form, we want to take a look at all of the fields in the parking tickets table and make sure that they are related or they are functionally dependent upon the primary key. So let's take a look at parking tickets table. The primary key is the parking ticket number. The ticket data is related to the parking ticket number. The code is related to the parking ticket number. However, the fine and the explanation are not. Actually, they are related to or dependent upon the code number. So to correct this problem, we're going to create a third table. And we will put all of our violation codes in that third table, and we'll call it the parking violation codes table, and it'll have a primary key of the parking code. And again, I'm going to add a foreign key to the parking tickets table to allow us to relate all three of our tables now. In terms of Microsoft Access, visually at the bottom of this slide, this is what this relationship looks like. We have car registrations that are related to many parking tickets. We have parking violation codes that occur on many parking tickets. So we have two of these one-to-many relationships. But we are now in third normal form, and we have created a well-designed database.